Hello, this is Mr. Math Guy, and today we are looking at graphing polynomial functions. So looking at the do now, I'll do number 1 with you guys, and then you guys can do 2 and 3. So it says determine and explain the end behavior of each of the following functions. So end behavior is just exactly what it sounds like. It's the behavior at the ends of the graph. So we have the left end, which is here, and then we have the right end, which is here. So if I look at what's going on in the left end behavior, what's happening here is to start with what's happening with the input, the x. So as we get further and further left, we add arrow, that x is going to be getting closer and closer to negative infinity. So as x approaches negative infinity, that's what that little arrow there means, approaches. So as x approaches negative infinity, what's the y getting closer and closer to? Well, it keeps on going up. So the y is going to approach positive infinity. Now think about why that's the case. What is, in this equation, what is impacting our output the most? It's that x squared. So if we have, say we plug in something that's close to negative infinity, let's plug in negative 1,000 squared minus 5. That's just going to be positive. That's going to come out to be a very large positive number, because that negative 1,000 squared is 1 million. So 1 million minus 5, that 5's not doing too much for us once we get to a very negative number. So this outweighs, the million outweighs the minus 5, and we're going to keep on going up at a very rapid pace. So this is because the x squared is a term that impacts the output the most, and as x approaches negative infinity, like we had a very small negative number there, y continues to increase because the x squared is positive. And then if you look at the right end behavior, it's very similar. What's the x approaching on the right end? It's approaching positive infinity. And then the y is also going up, so the y is approaching positive infinity. And that's for the same reason as we did above. You can think, instead of thinking of it as 1,000, think of it as positive 1,000. So instead of negative 1,000, think of it as positive 1,000. You end up getting the same exact number because you're just squaring it. And for the same exact reason, but the x is increasing. It's to positive infinity. The y is also going to increase to positive infinity. So I just want you guys to do number 2 and number 3. Take your time, no rush. Especially, really take your time with the explanation. Kind of think of, what's the highest degree term that's affecting our output the most as we approach what x is approaching on the left and the right. For number 2, we can say, look at the left end behavior. Here's our left end behavior. So you can see the arrow there. As x gets closer and closer, it's going to the left, so negative infinity. We're going down, so y is approaching negative infinity. And why is this the case? Well, as we get closer and closer to negative infinity, the term that's going to impact and drown out all the other terms, it's going to be the x to the third. Think about if we had like negative 100,000 to the third minus 3, negative 100,000 squared plus 2. Yeah, negative 100,000 squared is going to be a pretty large number, but negative 100,000 to the third is going to be a much more larger number. So that's going to really outweigh everything else. So as x is close to negative infinity, what happens to negative 100,000 times negative 100,000 times negative 100,000? Is it's going to be a really large, really small negative number, because it's a negative times a negative times a negative. So you get negative, which is a very small number. So that's going to make our y definitely very low and definitely very negative. So the y is going to approach negative infinity. And for the right end, the x is approaching positive infinity. So what's that going to be? What's going to happen there? These are all just going to be positive. And then it's just going to be positive times a positive times a positive. And that number, that very large number, is going to outweigh really everything else. And the y is going to approach positive infinity, as we see on the graph. Now, looking at number 3, it's a degree 4. So really, no matter what we put in for x to the 4th, it's going to be positive. So if we put in like negative 100,000, we can see as the x approaches, as we go to the left, as x approaches negative infinity, the y is going to keep on going up. So the y is going to approach infinity for that same exact reason as above. The x to the 4th is what impacts the output the most. So as x approaches negative infinity, think of a really small negative number like negative 100,000. If you were to raise that to the 4th, that's going to be a very large positive number because we have a negative times a negative times a negative times a negative, which makes a positive. And for the same reason, if x approaches positive infinity, that's still going to be a positive number. So y is going to approach positive infinity. Let's go to the next page. On the next page, I just want you guys to pause the video and try doing this one, both the left end and the right end behavior. Play the video once you're done. So when I look at the left end behavior, so same thing, look all the way to the left. Here's all the way to the left for us on the graph. The x keeps on going to the left. So as the x approaches negative infinity, the y is also going up. So the y is approaching positive infinity. So the x is going to the left, negative infinity. Y is going up, positive infinity. Why is this the case? Well, the x, negative 2x to the 3rd, is what is going to impact the output the most. So let's plug in like a really negative number. Negative 10 is not that close to negative infinity, but no, when you plug in negative 10, you get negative 1,000 because a negative times a negative times a negative, but when we have that Lie coefficient being negative, what's going to happen here is that we're going to have to multiply by another negative, and that transforms that into a positive. In this case, positive 2,000. So if there's a negative Lie coefficient, it kind of swaps everything up. And when you look to the right end behavior, the x is getting closer to positive infinity. The y is going down, getting closer to negative infinity. Why is that the case? Because that is, like we said, that first term, the highest degree, is the term that's impacting the output the most. So when I plug in something close to infinity, which 10's not that close, but I chose to show 10, we have a positive 10 times a positive 10 times a positive 10, which is positive 1,000, but then we have that negative 2 out in front. So the whole explanation there, I was trying to show you guys why it's the case for the end behavior of any polynomial rules. So this is very important. Start this. Make sure you are good with this little vocab breakdown here. So what it says is the end behavior of any polynomial is determined by its degree and the sign of the Lie coefficient, which we have been looking at. We've been looking at the highest degree with the Lie coefficient. So if P has an odd degree, so if the polynomial has an odd degree, if it's an odd degree polynomial, it looks like this, or it looks like this, and it all depends on what the Lie coefficient is. So if the Lie coefficient is positive, then we're going to start down here. So we start in the lower left, and as x approaches negative infinity, the y is going to approach negative infinity, and then we end all the way in the top right. So as x approaches infinity, y approaches infinity as well. But if there's a Lie coefficient, that means that all gets swapped. Think about Lie coefficient with a quadratic or absolute value. It just flipped it over the x-axis. That's what's happening here. It's getting flipped over the x-axis. So it would behave in the opposite way. So I always think of it as an odd degree. So if the polynomial is an odd degree polynomial, the end behavior is going in opposite directions. But if it has an even degree, think about, we've done this before, even degree polynomial is a quadratic. A quadratic could be one of them. So we know that's ending, it's either both going up or both going down. So that's for all even degrees. And if the Lie coefficient is positive, going up, opening upwards, you could also think of it that way. If the Lie coefficient is negative, it's opening downwards, much like if it was y equals negative x squared, that would open downwards. So those are the rules for the end behavior of polynomials. Can't stress enough, star this, make sure you guys are good with this. And let's go to the next page. So we want to sketch the graph of this polynomial f of x. So first thing we do, we have to find all the intercepts. So we have to find the x-intercepts and we have to find the y-intercept. So x-intercepts, it's when the y is equal to 0. So just set it equal to 0, and look at this, it's already factored for us. So we can just find each 0. So this would be x equals -3, x equals 4, and x equals -1. So we found the x-intercepts. Now we just have to find the y-intercepts. And how do we find the y-intercept? That's when the x is equal to 0. So we would have set the x equal to 0. And just looks like we're just going to be multiplying it through. We should get 3 times -4 times 1, which is -12. So our y-intercept is 0, -12. So when we sketch it, was plot all those points. We got -12, we'll say, is down here. We have x-intercepts of -1, -3, and +4. So there's two methods we could use. We could use method 1, which I like to use method 1. We could use the end behavior method, or we can test points if you forget the end behavior. So if we look at our function, if you want to multiply it out, go right ahead to see put it in standard form. But what degree do we have? Well, we have x times x times x. So that is going to be a degree 3. And degree 3, our Lie coefficient is just going to be x times x times x. So our Lie coefficient would be x to the third after we multiply it all out. That has a positive Lie coefficient. So our graph is going to look something like this. So if we look at the end behavior, as x approaches -infinity, that x to the third is also going to be negative. So that's y is going to approach -infinity. And as x approaches positive infinity, the y, x to the third, is going to be positive. So the y is going to approach positive infinity. So that helps us know where we're going to start. So we're going to start in the bottom left, because as x approaches -infinity, y is also approaching -infinity. So they're both going to be negative. And then for our sketch, these are the x-intercepts. So they're crossing at the x-intercepts. Cross. And then we have to come back down to cross again. Make sure you get to the y-intercept. Cross that. And then we have to also get to this x-intercept. And now it just keeps on going up. Make sure you put your arrows. And that's all you need to do for the sketch. Not the neatest sketch in the world. We're just sketching. Doesn't really matter. And method 2, we could also test points. You don't have to do it this way. I like the other way. It's a lot easier once you get down to the end behavior. But it's kind of what we did for the inequalities. So we put our x-intercepts here. And you want to just test points on each, test -4, maybe -2, 0, and 5. And you can plug those in to our equation. And we can see when you plug in -4, you would get a negative times a negative times a negative, which would make this negative. and then this will be positive, negative, but plug in each of those points, kind of exactly what we do with quadratics, and that just means our y starts in the negative, then it crosses to the positive, crosses again to the negative, crosses again to the back end to the positive. Oh, one thing I want to do, I just realized I did this. I'm going to erase this one because it's not like bouncing there at the 12. It should be a little bit more to the right, so I should draw it more like that's better. Because it's not gonna bounce right there at 12. If you're like, oh, how did I know that? Because technically, here's -1, here's 4. It's gonna bounce like exactly in between that, so it should be there's 5 in between there, so it's gonna technically bounce at like 1.5, so the midway marker between. I mean, for sketching, it doesn't have to be perfect, but that was a little too off. That's not bouncing at the 12. So what I want you guys to do for A and B, choose whatever method you want. I recommend method 1. And sketch each of them. And make sure you check in your calculator at the end, because I know B can be a little tricky, and we'll talk about B a little bit in a second once I show you guys the work. But pause the video and play it once you're done. So, looking at A, for A, we want to sketch. So we first have to find the x-intercepts. That's what we're doing here. Set equals 0, factor, plot each of those x-intercepts there. I forgot to find the y and label the y-intercept, but when you plug 0 in for x, you just get 9. So that should be a 9 right there. And why does it look like this? Well, what's the degree of our polynomial? It's an even degree. So it's going to be both going the same way, both going up or both going down, both end behaviors, but it has a positive lead coefficient. So it's both going to be going up. So it's, well, I guess technically the math words would be as x approaches negative infinity, the y is going to approach positive infinity. As the x approaches positive infinity, the y is also going to approach positive infinity. So that's why we want to start up here. And then we have to cross at every x-intercept. Cross, and voila. That would be our sketch of A, g of x. Now, B's a little tricky, and that's kind of leading into what we're doing. That's why I say check in your calculator. B. When you look at B, we have to find the x-intercepts. But when you find the x-intercepts, what is slightly different than what we just did on A? Look at x minus 3. That is a factor, but it's a factor twice. So technically there's 2 zeros at 3. They're just the same. They're both 3. So that is why it looks like it is bouncing, because it is bouncing there, because it has an even number of those zeros. Think about what like y equals x squared looks like. It looks like this. And the only 0 there is 0. And it's bouncing off that 0 because there's technically 2 zeros at that 0. That's what's going to happen with our polynomials. If there's ever an even amount of those zeros, like in this case, it bounces off it. And that's why I want you guys to check in your calculator as well. But let's talk about the end behavior as well. It's a odd degree, so it's going in the opposite direction, either this or this. But why is it looking like this? Well, because it has a positive lead coefficient. It doesn't have a negative lead coefficient. So we start here. We cross at the 0, which also has to happen to be 0. And then we go back down because at 3, it's not crossing. Although if you made a cross, like I understand, like almost everyone does that because it's the first time doing this. It's bouncing there. And then it goes back up. And it would bounce there. It behaved like slightly differently, which we're going to go over the next page. If it was like a degree to the 4th, or if it was to the 6th, or the 10th, or any even degree for that 0, it's always going to bounce. And that is the shape of the graph near zero of multiplicity M rule. So multiplicity just means how many times that zero is happening. So if the multiplicity is odd, so if it's 1, 3, 5, so if it's like x to the x minus c to the 5th, it's going to cross. And if it's like x minus c to the 10th, it's going to bounce. Because if the multiplicity of that 0 is even, it's going to bounce. The only thing that like changes a little bit is we'll talk about it. We'll talk about it once we do A. But any odd multiplicity, odd amount of that same 0, it crosses. Even, it bounces. So let's look at the next question. So we want to sketch A. So whenever we're sketching, we got to think of, let's find all those intercepts. So let's first start with the x-intercepts. Why not? So we're going to set this equal to 0. And now we're just going to solve. So we got x to the 3rd, x plus 2, x minus 3 squared, and 4x minus 3. So let's look at what all of our zeros are going to be. It's a big T-chart. We have a 0 of 0. We have a 0 of negative 2. We have a 0 of 3. And we also have a 0 of 3 over 4. So that's our x-intercepts. Let's look at our y-intercept. If I plug in 0 for everything, well, these numbers aren't going to be 0, but this is. So if you were to plug in 0, our y-intercept is just going to be 0, 0. So let's take a look at what our sketch is going to look like. So it's going to cross at 0, 0. Because that's our y-intercept. And then let's do our x-intercept. So we have an x-intercept also at 0, so right there. We have an x-intercept at negative 2. We have an x-intercept at 3. And then we also have an x-intercept at 3 over 4. Okay, so we plot all our intercepts. Now we have to look at how the graph is going to be behaving. And in order to see that, we have to look at, I always look at the degree of the polynomial first. So the degree of the polynomial, think about it technically, you can think about how many zeros there are, or look at the exponents. So we have an x to the 3rd, we have a x plus 2 to the 1st, then squared, and then a 4x minus 3 to the 1st. So if I want to look at the degree of this, we could multiply it all out. That's a lot of extra work. Or we can just look at how many zeros there are or add the exponents up. So we have 3 plus 1 plus 2 plus 1. So this is a degree 7. And our Lie coefficient, there's no negatives in sight for those x's. So our Lie coefficient is positive. So that means it's an odd degree, and our Lie coefficient is positive, so it's going to look like this. As x approaches negative infinity, the y is also going to approach negative infinity. But as the x approaches positive infinity, the y is also going to approach positive infinity. So that means we're starting down here, and then let's look at each multiplicity of the zeros. So here, my first 0 I'm going to be crossing is negative 2. That multiplicity is 1, an even multiplicity, so I'm just going to cross. And then I'm going to come back down to 0. At 0, I also have an even multiplicity. So this is where it's a little bit different when, so like as we get to a higher degree multiplicity, so here the 0 is happening 3 times here, you don't have to be super perfect with this, but what's going to happen is it doesn't like simply cross. It kind of like gets close, and you can see it kind of behaves a little like that. You see it has that little like, it gets like a little flat towards the 0. You know, I don't have to be. I'm not super picky on that, but that's just how it would look as the multiplicity goes up. And then 3/4, it crosses again because that's an odd multiplicity. And then at 3, here's the winner. It is an even multiplicity. So what happens when it's an even multiplicity? That's when it bounces. So we're going to be bouncing at tree and then going up. So that's what our sketch should roughly look like. And actually, let's have you guys do B also behaves a little weirdly. But pause the video and play it once you're done with B. So here's what it should look like for B is degree 3. So it's got to start, and with a Lie coefficient, so it starts here, ends up here. And then the weird thing about B is it only has one real zero, one real x-intercept, or any x-intercept. So that's why we have it only crossing at -2 once. And if you graph this in your calculator, which I highly recommend doing, you're going to see there's like this little kind of like bumper curve right there. And that's kind of telling you there is an imaginary solution. So if it looks something like this and it crosses, but then it has like a weird curve right there, it doesn't like cross again, that means there's going to be some imaginary solutions there. So that's why it looks kind of... Oh, wait, that's the next question. So why do you think it only crosses the x-axis once? It's because it only has one real zero. The other zeros are imaginary. So let's go to the next page. On this page, so this is the last one of the notes. We're not sketching here. We are actually graphing with accuracy. So one thing I'll say before you guys get started on this one, be very careful with the vertices. There's multiple here. And make sure they're plotted as perfectly as possible. So there's a way of doing that. Think about how we did that graphically if it wasn't like on our table. So pause the video, play it once you're done. So first find the zeros algebraically, set equals 0, and just do your factor by grouping. And then graphing, I would just do the XY table. But here's the thing almost everyone doesn't do the first time. Is you have to make sure you plot your vertices, which are here and here. They're not shown on the table. Especially here, people go wrong. So when you're graphing this, make sure we're not crossing anything we shouldn't be crossing. Like, don't cross the x equals 3 line, because that's going to be 3 comma something else. But when you're finding these vertices, how would I find these vertices using a calculator? What you could do is second calc, and then this is a maximum. Go a little bit to the left, press enter, a little bit to the right, press enter, and then enter as close as possible, and it will give you that vertex. You don't have to include in the XY table, but you do have to plot it. And you got to do the same thing down here, but it would be a minimum instead. So be careful with that. Honestly, if you didn't do that, I guarantee you almost everyone, if not everyone in class, did that. Did not find the maximum minimum like that. So, like, make sure you do that. Everyone always forgets that, how to do that, especially with polynomials. But make sure when you're graphing now, and we are not sketching. Sketching, is just a quick sketch. Make sure it's kind of accurate. It doesn't have to be perfect. But when you're graphing, it does have to be as close to perfect as possible. So you have to graph those vertices. That's it.